the probabilistic assessment, you actually get the solid red line. It's not as important at low return periods, but at long return periods, that you could greatly underestimate the actual response. They know that not everyone's going to be able to do a fully integrated probabilistic implementation of nonlinear site amplification, so they found that this modified hybrid approach, which is much simpler, that is in Goulet and Stewart 2009, actually works pretty well and captures the solid line. So think about that if you are doing site response at long return periods and you are doing it the conventional way of doing deep soil analysis given a probabilistic outcropping rock motion. In terms of soft plate seismic response, key modeling issues, probably one of the most important things to capture is the shear wave velocity profile, including obviously the thickness of the clay and the spatial variability. I find that often methods like surface wave methods give you a shear wave velocity that is resolved as being something like that, constant velocity over some depth. We know the principles of soil mechanics and effective stress means that stiffness has to increase with increasing vertical effective stress. So even though I might measure a line, if it's a thick soft clay, I know I should use increments in shear wave velocities that increase with depth. You will get a higher response with that yellow characterization versus the white characterization. It's analogous to what Professor Kramer was talking about in terms of topographic amplification. Every time you hit an impedance contrast, you're sending more energy up and less down. And so having the shear wave velocity vary incrementally will give you a more intense, more accurate answer. Obviously, capturing the peak dynamic undrained shear strength is important. We talked about that the first day. So remember, rate effects will increase the strength, cyclic degradation will decrease the strength, so you have to look at those two competing things to adjust your peak static strength to your peak dynamic strength. If you get large deformations in the clay, then you can't use peak strength. You probably have to use residual strength. Make sure you adjust your GOG max curves, as I'll talk about. The first thing I look at after a deep soil or shake analysis is the shear strength profile. Before I look at PGA versus depth, response spectra, I want to see where am I getting large strains? Are those large strains concentrated in the areas where they make sense? Am I getting some irregularity, like at depth? Way below the soft clay, am I getting a concentration of strain in a layer just because of the way I modeled it? I put in a shear wave velocity profile that has a little kink in there, and that led to an iteration where we had too much strain in that layer, which softened it, which led to too much strain, which softened it. You look at those things. So look at the shear strain profile first and say, is it reasonable? Then always compare your results with the empirical data and the simplified methods. So the work I cited earlier in this talk. Most importantly, as I mentioned before, if you're doing a shake or a deep soil or a fully nonlinear analysis at high intensities, that's a very difficult thing to do. Always pull back, take your design ground motions, divide them by 10, and just run those motions up and make sure that you can capture the response that we know you're going to get because we have empirical evidence at low intensity motions. And make sure you're getting that right. And it's kind of nice to just progressively increase your motions and see how you're following that bend over curve. And there might come a point where all of a sudden things go way bad, they go bad, then you can catch that and find out what's the problem. As Professor Kramer mentioned, a key element is to actually modify the tail of the GOG max just ever so slightly so that you match the strength of the material. If you underestimate the strength of the material, you're potentially going to be unconservative because you're going to base isolate and not get as high a response. If you overestimate the strength of it, you might have the wrong period, and you might actually be overly conservative. So just make sure you adjust your G or G max curve so that the strength is captured. DMOD helps you do that well. In terms of seismic performance of soft clays, we had pile-supported structures at the airport in Mexico City, and of course, that's not going to go down. The clays have been settling, undergoing seismic compression. When an earthquake comes along, the seismic compression and settlement that may have happened over the next 10 years happens all at once. And so you get these kinds of sudden settlements. That makes sense in the free field next to a pile-supported building. What was also interesting, and it's documented very nicely in the GEAR report that Juan Mayor led, is there were areas where at certain edges of the basin where the material was settling and settling, and then this earthquake came along and popped it, and all of a sudden we got strain concentrations. And so there were ground failure that we believe is because of the long-term buildup of a stress concentration, and then all of a sudden the earthquake allowed it to basically be expressed at the ground surface. Of course, there are problems with foundations on soft clay. This is an overturned building in Mexico City during the '85 earthquake. The same formula I talked about earlier, it's more appropriately done for clays. And this is pseudostatic, so it's essentially saying if I lose strength in my soft clay because of cyclic degradation from the subduction zone earthquake, if I use my post-cyclic undrained shear strength of that soft clay, a good first check is the factor of safety close to 1 or less than 1 without inertia effects. There was some nice work done by Alain Pecker and his student in France, where they looked at pseudostatic bearing capacity analysis of shallow foundations on soft clay. And what they found is you should focus on the reduction in the shear strength due to cyclic softening of the foundation clay. That's something I already talked about. And the other key effect is obviously a design-based shear combined with the weight of the building leads to an inclined load, which changes the failure mechanism, and they found that it was critical to include that inclined load from the base shear being added on to be able to capture the performance of the clay. Importantly, they said, you don't really have to worry about the inertia effects of the clay itself. They did a sensitivity analysis and showed that it was unimportant. In terms of piles, again, some of the very best work that I've seen, because I've worked in Mexico. Unfortunately, I haven't worked in Colombia yet, so I'm not aware of all the work that you have done. But this is a nice piece of work demonstrating Mexico City's clay has a large volumetric threshold strength. Yours is probably a little less than that, but that gives you a large range of deformation that displays nearly elastic response. Once you go across that, you remold the clay at constant volume, you actually drop the strength by about a half. What was interesting is they did some pile load tests with vertical loading, and if the maximum load of the experiment did not exceed their design load, there was essentially minimal movement, negligible movement. After 30 cycles of loading, less than 5 millimeters. When the load barely exceeded that, they started to get an increase in settlement. And when the applied vertical load was just 1.15 times the design load, so just 15% more, all of a sudden large settlements occurred. And then actually when they recapped the piles, the capacity had reduced to 80% of what they measured originally. So that's another indication of the kinds of things that you can have. Last but not least is this is a project in the San Francisco Bay Area where there is soft young bay mud. It has sand at the top and stiff sand below that. And these are the calculated pile response, or the pile demands, not due to a lateral spread or a slope displacement movement, but just large transient deformations. And so you see, for example, the deformations in the clay unit is on the order of about 90 centimeters. That leads to large shear demands, which are shown here, that are on the order of about 310 kilonewtons, and it leads to a large bending moment. And you can see that in terms of the shear demands and leading to the bending moment. And that transient response is actually going to control the design of those piles. And it's not from permanent loading, it's transient. So in summary, soft clay site response can contribute to localized damage. We see it over and over again. The empirical evidence indicates amplification of the low intensity motions. We do get de-amplification at the higher intensity motions because we can get so much damping and hysteretic energy being eaten up. You can get large strains, especially for intense levels of shaking. And remarkably, 1D analysis can capture many of these things. So at least start with the simplified empirical methods, do 1D analysis, and then venture into 2D, 3D. In terms of foundation performance, we saw ground cracking and differential settlement in the Mexico City Basin from the 2017 earthquake that I think should be carefully looked at, where you have transitions from the edge of the basin to outside the basin, or differences in thickness of the soft clay within the basin. You evaluate bearing capacity considering strength loss and the inclined load. The other aspects are less important. And you can get large demands on piles due to the transient loading, especially at the contacts between stiff and soft soils. Thank you very much. I think the best thing to do is have Professor Kramer present his lecture, and then he can have the left mic and I'll have the right mic, and we can answer questions.